my friends, welcome to the next lecture on magnetostatics. So in this lecture, I will be completing the magnetostatics topic. So in this lecture, basically I have divided this lecture, this will be a long lecture and I have divided it into two parts. In the part one of it, I will discuss what is Ampere's circuital law, how do we use the Ampere circuital law. And in the second part of the lecture, I will be discussing about the magnetic moment, which is also I have seen many questions coming from magnetic moment as well. So let's begin. So Ampere circuital law is a very beautiful mathematical law, which makes finding the magnetic field much easier. So many times it is difficult to find the magnetic field using Biot-Savart's law. Right. So till now we have studied the Biot-Savart's law through which we can actually find the magnetic field. But in some cases, Biot-Savart's law becomes a little difficult problem, and Ampere circuital law is much easier way to find the you can say your magnetic field. So what is the statement of Ampere circuital law? So the closed line integral. So first of all, you have to close a line integral in the magnetic field. So let's say you have some magnetic field and you close a line integral. So you can clearly see this is your path. You can actually see your circular path, and this is a closed circular path, and it's a line path. It's a line closing it, some path. So B dot dl. So we have to do the line integration of B. So we are doing the line integration of magnetic field. So basically we are finding, so what we are doing actually here is, let's say at this moment, you are moving in this direction. So this is dl vector. And let's say it's not true, but let's say magnetic field is here. So at this moment you will do B dot dl. Okay. Again, you will do the same process here. Again, you will do the same process here. Again, you will do the same process here. So you will do the B dot dl everywhere on the point on the path. So once you do that, what you will find is then you will sum all of that, or you can say you will integrate all of that, and then that is the basic definition of B dot dl. So basically you are doing the line integration of magnetic field, and that path along which you are doing the integration is closed. So this will always be equals to nu naught times current enclosed in the path. For example, in this case, you can actually see if I do the B dot dl in this situation, how much current is enclosed in it. So this dot means the current is coming out. So 1 ampere current is coming out. 2 ampere current is coming out. So 1 ampere is coming out, 2 ampere is coming out. So current coming out is taken as positive. However, the 1 ampere current is going in, and the current going in is taken as -1. So the total current enclosed is 2 minus 2 epsilon naught, right? 3 minus 1 is 2. So basically your B dot dl in this situation will be -2 mu. This is our integral form of Ampere's law. So this form of Ampere's law is known as integral form. We can also write our Ampere law in the differential form. How? So this is our law which we are familiar with. Now I will use a Stokes theorem. So the closed line integration can be written as del cross B into open area dA. Right? This is Stokes law. Stokes theorem says A dot dl can be written as area integration of del cross A dot dA. So basically I have written B dot dl as del cross A dA. On the right hand side, I have kept nu naught I enclosed. Now, I enclosed or the current can be written as J dot dA. J is the current per unit area. And I am basically multiplying with my area so that I will get the small current. I will get the small current DI. And if I do its integration, I will get the total current. So basically the current can be written as J dot dA, where J is the current density. I have already discussed about current density. What is current density? J is the current density, which is also known as current per unit cross-sectional area. Current per unit cross-sectional area. I have discussed already about this. How you write J, how you write K in my vector potential lecture. So basically I replace my nu naught I enclosed by nu naught J into dA. So now you can clearly see on both sides there is an area integration. So basically what I can do is I can write my del cross B as nu naught into J. So my del cross B can be written as nu naught into J, where J is the current density and this is your differential form of Ampere's circuit law. You should remember this statement, very important. Now it is time that we learn that how the Ampere circuit law is actually useful. Okay. So in order to do that, I will be considering the three examples, and in these three examples, you will completely understand that how you can implement the Ampere circuit law. Let's consider the first statement, and that statement is, or the first application is hollow cylindrical wire. So there is a wire which is hollow from inside. Usually this never happens. It's a very rare event, but this can happen. So let's say there is a hollow wire. There is nothing inside it and all the current is flowing on the surface. So on the surface of the wire, the current is flowing. So we need to find the magnetic field because of this situation. We need to find magnetic field inside and as well as outside. Now this is a very simplest problem and we can find the magnetic field. Why? Because any current carrying wire behave as a magnet or produces the magnetic field, and that is exactly the magnetic field we want to find out. So let's first figure out how you will find the magnetic field inside. So if I want to find my magnetic field inside, so first step that I will do is I will consider the Amperian circular loop. Amperian circular loop is a hypothetical mathematical loop which has a radius small r, and this radius is lesser than capital R. Capital R is the radius of the cylinder. So you can actually see that I have taken one empirical cylindrical, circular loop inside the cylinder. That's it. So I have taken so whenever you have the cylinder, so whenever you have the problem of cylinder, take the circular loop. So consider the hypothetical circuit. So how much current is flowing through this circular loop? So answer is no current. Because the current is on the surface, there is no current inside the cylinder, so that hence there is no current which is flowing through this circle. So the current enclosed through this loop will be zero. So if the current enclosed through this loop is zero, so B dot dl will also be zero, and hence magnetic field will also be zero. So magnetic field inside is always zero in case of hollow cylindrical wire. Now, what about outside? So now again, I will take the empirical circular loop, but now the situation is now the radius of this loop is greater than my capital R. Now, how much current is flowing through it? So the current I is flowing in the conductor, and this current I will come and pass through this bigger loop. So this will pass the bigger loop. So the current enclosed in this bigger loop is I. So current enclosed in this bigger loop is I. Okay. And then I will say B dot dl equals to nu dot I. Now, how do I resolve this? Now, I already told you if you have a wire, then the magnetic field because of this look like a circumferential, right? You remember the rule I said, clockwise and anti-clockwise. So if the wire is there, then the magnetic field is circumferential, means it is rotating around the wire. So this is how the magnetic field lines look like. So you can clearly see that this is a magnetic field which you are seeing here, and it is circumferential. Similarly, your DL means you are moving on this wire, in this circular loop. So DL is also flowing like this. Magnetic field is also like this. So B and DL are in the same direction. So if B and DL are in the same direction, I can say B dot DL is B DL, cos of angle between them. The angle between them is 0 degrees, so cos 0 is 1. So B dot DL can be written as BDL. So this is B dot DL I have written as BDL equals to nu dot I. Now the magnetic field depends upon two things. One is current and another is the distance from the axis. So the current is same for all the points. If you have for this point, the current is flowing through the loop, so it doesn't matter. But and also the distance from the axis to all these points will be same because all of them are lying on the circumference. So if I have a circle and this is my center of the axis, all these points are at the equal distance. So magnetic field will be same throughout the circular loop. Whatever is magnetic field here, the same magnetic field will be here, same will be here, same will be here. That is why the magnetic field is constant throughout the integration. So I can take my magnetic field outside. And if I take my magnetic field outside, then inside you will left is closed integration of dl equals to nu naught I. This is the integration of all the small elements. If I combine all the small elements, I will get the total circumference, and the total circumference is 2 pi r. So basically, I will get B into 2 pi r equals to nu naught I, and magnetic field will come out to be nu naught I by 2 pi r. This thing we have already derived from Biot-Savart's law also, that if you have an infinite wire, the magnetic field because of that wire is nu naught I by 2 pi r. But this process made the derivation much simpler. Ampere circuital law makes the derivation much easier as we compare to the Biot-Savart's. Okay, now let's move to the second step, which can only be solved through the Ampere law. We cannot find the same derivation through the Biot-Savart's. So let's see. Now I have a uniform solid cylinder. Means my cylinder is uniform and the current is flowing throughout the cylinder. It is not just flowing on the surface, but inside also the current is flowing. And current density is given to you. So the total current per unit area is given. So the total current in the wire is I, and this area, cross-sectional area, is pi r square. So you always divide current with the cross-sectional area. So this current has a cross-sectional area, this pi capital R square. And since this current is flowing along k cap direction, so the direction of J vector is k cap. Now, first thing first, we will find the magnetic field inside. So again, repeat the same step. Consider the empirical loop. And I need to find the current through it. Okay, current enclosed. The total current in the loop is, or in the cylinder is I. So the total current in the cylinder is I, and I want to know how much current is flowing through this small loop. The total current through this bigger loop is, this bigger cross section is I, but I want to know how much current is flowing through this smaller loop. Always remember, I enclosed has two formulas. Number one formula, if you have uniform current density. For example, in this case, we have uniform current density. Current is uniform here. Whatever is current here, same current here, same current here, same current here. So it's a uniform current density. In that case, what you do is you simply multiply your J with the area that you have taken, this area. So you simply multiply by J with the area. But if you have non-uniform current density, for example, here the current is different, here the current is different, here the current is different. Then what you do is, then you use the formula of integration where you say J dot dA integration. For the similar thing that we done in the differential form of Ampere's circuital law. So in general, current is J dot dA, but if in general, your current is always J dot dA. But if it is uniform, then you can write this thing as JA. In our example, the current is uniform. So we will use the first formula, which is J into A. So I multiply J with A. J is current per unit area, which I have already find out. It is I by pi r square. I by pi r square. Multiply by the area that I have taken. So you have taken this area. This area is pi into small r square. So the current enclosed is I into small r square divided by capital R square. Okay, fine. Now I am ready to find my using my Ampere circuital law, I can find my magnetic field. How I can do that? So basically, I will be doing B dot dl integration equals to nu naught I enclosed. This is my Ampere circuital law. B dot dl integration can be written as B into 2 pi r, and nu naught I enclosed can be written as nu naught and I enclosed value I have inserted. So from here, my magnetic field will come out to be nu naught I into small r divided by 2 pi r square. Okay, so your magnetic field depends directly on R. Okay, and I am not doing the outside case. Outside case is very simple. Outside case is same. So inside I have found out that it is equals to nu naught I R by 2 pi R square. This is my inside case. For outside, the result will remain same, which is nu naught I by 2 pi R, and my R is now outside. Because in this case, nothing will change. The current enclosed will still be I. Because if I take the bigger loop, the current enclosed in this will be the total current, which is I. That's it. So nothing will change. Okay. So this is your situation. So if I try to plot the graph, what will happen? First, it is linearly proportional and then it is following 1 by r. So this is your how your graph will look like, right? So this was the second application of Biot solution. First we did for the hollow cylinder, then we did for the solid uniform cylinder. Now we will go towards the non-uniform case. So now still you have the cylinder, but now your current density is not constant, it is non-uniform. So you can clearly see that your current density depends upon R. It means if my R is small, my current density is small. So here current density will be less, but here current density will be more. So as I move away from the axis, my current density keeps on increasing. So now I have the non-uniform current density. In this case, what will be my I enclosed? So my I enclosed will be J dot dA. J is given to you. What about dA? So I have taken the small empirical loop. What will be the area vector of this loop? Perpendicular to this area. So area vector is always perpendicular to the area. So if I carefully see what is a perpendicular to this area, what will be the perpendicular to this area? That will be this direction. And so the area direction and the current density direction is same. So my J dot dA integration can be written as K R square J cap. So I put my value of J. I put my value of dA vector, which is dA in the direction of Z cap. So Z cap dot Z cap is 1 because now your J and area vector both are in the same direction. So basically you get K R square into dA. In case of cylinder, or you can say in case of this disk kind of situation, this circle kind of situation, the small area can be written as 2 pi r into dr. Small area can be written as 2 pi r into dr. How? So in this entire disk, what I'm doing actually here is I am taking the small thin ring having the radius small r and thickness dr. So what will be the small area? It will be length into thickness. So length is 2 pi r into thickness is dr. So whenever you have the disk, so this is a situation of disk, and we want to know how much is the total current flowing through it. So it's just a sort of a disk. So what I will do is, in always in the case of disk, the small area can be written as 2 pi r into dr. So dA can be written as 2 pi r into dr. So basically what I can do actually here is, I can take my 2 pi k outside. Inside I will get r cube dr. And my this disk is going from 0 to r. My radius is going from 0 to r. So my radius is going from 0 to r. So basically what I get is 2 pi k r cube dr, and my integration is from 0 to r. And if I do with this integration, I will get 2 pi k by 4 r raised to power 4. Okay, and this 2 I can cancel. So I will get my charge enclosed or my current enclosed as pi k r raised to power 4 by 2. Now I am ready to use my Biot-Savart's law, Ampere's second law, which is B dot dl equals to nu naught I enclosed. B dot dl can be written as B2 pi r, and nu naught I enclosed can be written like this. Nu naught is written like this, and the current enclosed I have written as pi k r raised to power 4 by 2. So from there, my magnetic field will come out to be nu naught k r cube by 4. Nu naught k r cube by 4, which is my option number B. So in case of non-uniform current density, all you have to do is you have to write your current enclosed as J dot D. That's the only difference that will come out. Okay, fine. Okay, so this was the 3 applications for cylinder. One was hollow, another was uniform solid, and third was non-uniform solid. Now I'm going to give you another application, but this is a different application, and this is for the current carrying sheet. Now you have the sheet. You have a sort of sheet. So now your current is flowing in a sheet. So you have a conductor sheet. So you can clearly see this is a sheet. And your current is flowing in this direction. Means your current is coming in x-axis. So your current is coming in x-axis. And since the current is flowing in the sheet, the value of K vector is given. This is known as surface current density. Surface current density. The direction of surface current density is same as the direction in which the current is flowing. So the current is flowing along x-axis. So the surface current density has a direction along x-axis. However, the magnitude of the surface current density is current per unit length. For example, J is current per unit area. Similarly, the K is current per unit perpendicular length. So the current is flowing in this direction. So the perpendicular length to this current is along the y-axis, or you can say this length L. You can clearly see that the current per unit length, which length? Perpendicular length. Perpendicular to this current. So the length perpendicular to this current is L. So the K is given by I divided by L. So current is, so K is current per unit perpendicular length, which is I by L. Now it is time that we predict that in which direction our magnetic field will be in. So before we go into the calculation, I just want to predict that what will be the direction of magnetic field. So you can clearly see that this is a, I can think this sheet as a many parallel wires. 1, 2, 3, 4. This is what it has been done in the diagram. The entire sheet has been drawn as a 3 wires. And because of the wires, you know, we find the direction by right hand thumb rule. We keep our thumb in this direction of the right hand and then we turn our fingers. So if we turn our fingers in this situation, basically I will get this loop. So you can clearly see if I'm up the plane, means I am at z greater than 0, then your magnetic field is going in this direction, which is minus y cap. But if I'm down, means z less than 0, below the plane, then my magnetic field is going in this direction, which is along the positive y-axis. So if I am above the plane, my magnetic field is along minus y-axis, and if I am below the plane, my magnetic field is plus y-axis. How? So basically, I draw the circle, and then you can clearly see the tangent to the circle. And how to draw this circle? I think all of you should know that, and that is by the using the right hand thumb. In the case of sheet, whenever you have to find the magnetic field because of the sheet, then the empirical loop that you imagine actually is a rectangle, or you can think of as square or rectangle, anything you can imagine. So imagine a rectangle. Half of the rectangle is above the plane and half of the rectangle is below the. Okay, so there are two rectangles. One rectangle. Half of the rectangle is above the plane and half of the rectangle is below the plane. And this solid side is above the plane and this dotted line is below the plane. So this I have shown here, and your plane is cutting it from the center. You can clearly see above the plane your I have made it reverse. Let me change the directions. Yes. So my magnetic field is in this direction. So I need to take like this. Sorry. Yeah. Wait a second. Let me draw with the black pen. Okay. So below the plane, my magnetic field is along plus y, and above the plane, it is along minus y. So the loop which I should take is your anti-clockwise. So I take my loop as anti-clockwise. Now, yeah. So now I'm ready. So you can clearly see the length above the plane. So this length, let's say this total length is L. Length above the plane and magnetic field are in the same direction. So B dot dl will be BL. Then this length and this is perpendicular. So this will be 0. Then this length and length L vector, this L vector and this B is perpendicular. So again BL, and this length and magnetic field is perpendicular. So again 0. So total B dot dl will be 2BL. One because of this wire and one because of this wire. So total B dot dl will come out to be 2B. Now I will find the current enclosed. So current enclosed is K into length. Why? Because K is current per unit length and multiply by the length that I have taken. So I will get K into L. So my current enclosed in this loop is K into L. right? Why? Because K is current per unit length and I'm multiplying it with the length which I have taken. So that will give me the total current in my loop. Okay. So B dot DL is 2BL, nu not I enclosing nu not KL. So basically 2 LL I can cancel. So my magnetic field will come out to be nu not K by 2. It will be plus J cap if I'm below the plane and it will be minus J cap if I'm above the plane. But the magnitude will be nu not K by 2, where K is the surface current density. So I hope that you understood the idea of how to find the uh, current, or sorry, the magnetic field because of the sheet. Okay. So if you have got this idea, let's move to the question. So this is a question which I have already explained you the formula. So you have the current wire, uniform wire. So current is uniformly distributed. So it's a solid wire and the current is distributed uniformly. So whenever we say wire, it's a cylindrical wire. Wire is always assumed to be a cylindrical. There are 2 points. So the radius of the wire is A. Now there is 2 points. One point is inside A by 3 and another point is outside. So we will have some magnetic field here and we will have some magnetic field here. I basically want to find the ratio. So magnetic field inside we have find out is nu naught I R by 2 pi A square, and magnetic field outside we have found is nu naught I by 2 pi R. So this is what I can do. So magnetic field at A by 3, I will use this formula and I will put my R as A by 3. This is what I have done here. And then magnetic field outside, but for outside, I will use this formula and I will use my R as 9A. So this is exactly what I have done here. So here it should be 9A. Okay. It should be 9A. And if you do the ratio, you will get 3. So you will get the ratio 3. Instead of R, I will put 9A. And if you solve this up, the ratio that you will get is 3. So 3 is your answer for this question. So answer will be 3. Okay. So answer is 3 in this case. The only trick that was to be used here was that when you are finding the ratio, you have to use the formula for outside when you are taking the point outside, and you have to use the formula for inside when you are taking the point inside. Fine. So that was a simple question, but I have seen not many difficult questions are coming from magnetostatics. Basic level questions or the simple questions are coming in all the exams. Only thing is that you have done all the PYQs well and one problem sheet. That's it. You don't need much efforts in magnetostatics. Only thing is all the concepts are summarized at one place. That's the whole entire idea that you require. Okay. So till now I have discussed Ampere law. I discussed 4 applications, 3 cylindrical and 1 sheet, and then we did the question. Now a very tiny topic, which is boundary conditions. Without the proof, we don't have to get into the proof of all that because that is not necessary or required. You can read the book anytime. You can read the DJ Griffiths book and see that why these things are happening. Okay, I am not getting into that right now. The reason being that is not required for our exam purposes. Yeah, that's a good discussion that we can have, but not a good purpose for our examination. So what is a boundary condition for magnetostatics? So the perpendicular component of the magnetic field is always continuous. So whatever, so let's say you have some magnetic field in one side of the interface and another magnetic field on the other side of the interface. The perpendicular component, what do you mean by perpendicular component? The component which is perpendicular to the plane. So let's say this is Z plane, Z equals to 0 plane. So the direction which is, so the magnetic field along the Z axis will be continuous. So whatever is the magnetic field along Z axis on this side, that will be the same magnetic field along the Z axis in that side. So you can say B1Z and B2Z will be same. Okay. But however, the parallel components means X and Y components will not be parallel. So X and Y components will be discontinuous. So B2 parallel minus B1 parallel have some discontinuity, and how much discontinuous they are? Nu naught times K. K vector is the surface current density in this interface. So this is an interface which is So let me make this interface very nicely. So this is an interface which is dividing the two mediums. So if this interface have some current density K, if it does not have any current density, let's say no current is flowing in this interface, then the parallel components are also continuous because this thing will become zero and B2 parallel and B1 parallel will become same. But let's say this is not continuous, means this is the current is there. So some current is flowing in this boundary. So what will happen then? The parallel component of magnetic field here and the parallel component of magnetic field here will not be same. So B2 parallel minus B1 parallel will become nu naught into K vector. If I write both of these properties in one single equation, which is known as vector form, then I can say that B2 vector minus B1 vector is equals to nu naught times K cross n cap, where n cap is the vector perpendicular to the interface. So always remember these three formulas. Let's solve one problem that you will get a good idea of. So you have a z equals to 0 plane. So in one side you have given this magnetic field and on the other side you have given this. So what is the perpendicular direction? So z direction is your perpendicular and you can clearly see the magnetic field along z is same on both the sides. Here also it is 5j cap and here also it is 5z. Only difference is in parallel component. So this is a parallel component on one side and this is a parallel component on the other side. So I will use my equation, which is B2 parallel minus B1 parallel equals to nu naught K vector. Basically, they are asking what is the value of this K? What is the magnitude of this K? So I am doing B2 parallel minus B1 vector parallel equals to nu naught K. So B2 parallel is x cap plus 3y cap and B1 parallel is 3x cap. So from there, if you see that my nu naught K vector will come out to be minus 2x cap plus 3y cap, or my K vector will come out to be 2x minus 2x cap plus 3y cap by nu naught. If I try to find its magnitude, 2 square plus 3 square under root 13 divided by nu naught. If I put my value of nu naught, which is 4 pi into 10 to the power minus 7, and if using the calculator, which is allowed to me, if I find the value, I will get 2.86 into 10 to the power 6 amperes per meter. So I need to give the answer in terms of 10 to the power 6. So my answer will be 2.86, which is my correct answer. Okay. So simple boundary condition problem have been came in the exam, and one of the example I have already given you that how the question can come. Okay. So that is the situation. Okay. Now, in the next class, what I will do actually here is that I will pick up from here and I will teach you magnetic dipole moment. It's a very, very, very important topic. And magnetic dipole moment is something which is not written very well in your Griffiths book. I won't say very well. It is not even written. All the information is not written there. So this topic is combination of BSc and class 11th 12th. And the questions have came in NET, GATE and JAM exam. So I will be teaching this topic in the next class. That's all for today. See you in the next lecture.